Hello, this is Dr. Lori. Welcome back to our discussion on analyzing data for diseases that are rare. And so what we've already looked at in a previous video is calculating an odds ratio. We pretended to be epidemiologists and we calculated the odds ratio is equal to 234.3. I'm going to start with a new empty table, but we need to fill it in with the same information, basically, just because I need a little bit more space to be able to get everything into this table that I need. So I'm going to start off by filling in the bottom part here. This is where we start with case control studies. We know that we have 20 cases and 40 controls, so we have 60 people altogether in the study. And I'm going to do something a little differently than last time, and that is we know that we ended up with 22 people who were exposed and 38 people who were not. And you'll see why I'm doing this in just a minute. Before I fill in how many cases I actually had, one of the things that we want to do when we calculate a chi-square test of independence is we want to calculate how many we expected. I'll put E-X-P-E-C-T. We expected to have in each of these 4 quadrants. How many expected did we have that were cases who were exposed? How many expected did we have who were controls that were exposed? That would be this box over here. How many cases did we expect to be not exposed? And how many controls did we expect to be not exposed? Again, so we have our 4 different quadrants for those 4. Now, if exposure to this risk factor is not related to being a case or not, then we would expect it to be all balanced. And so the expected number can be calculated, and if you're kind of following along in terms of math, the expected number is equal to what's called the row total. So let's say we're calculating this top left box. It's equal to the row total, because this is the total of the top row, times the column total divided by the total. And so if I multiply 22 by 20 over 60, I end up with 7.3. And I could do that for all of the cells. If I take 22 times 40, that ends up being 14.7. This is my expected number. If I take 38 times 22 divided by 60, I end up with 12.7. And if I take 38 times 40 divided by 60, I end up with 25.3. Now, the other interesting thing that you'll notice right off the bat is that 7.3 plus 14.7 still adds up to 22. And 7.3 plus 12.7 still adds up to 20. So we're not changing the total number in any of the rows. We're just simply saying if this exposure is totally unrelated to being a case or not, this is how many we would expect to be in that top left column. Top left box, I mean. And remember also, this is kind of that box where the magic happens. This is where the disease is yes and the risk factor is yes. So we want to keep that in the top left box to be consistent across. Now, the number of cases that were exposed that we actually had was 19. That is a different number than 7.3. And the number of cases that were not exposed was 1. That is a different number from 12.7. Similarly, we can fill in the number of controls who were exposed and the controls who were not exposed. Now remember, this is fictitious data, again. But ideally, if there was no relationship between our risk factor and our disease, these numbers would be pretty close together. And the way we test that is that we actually calculate those differences. And somebody came up with an interesting way of calculating those. First of all, let's do this top left corner. They said, well, I wonder how far away it is. So they took 19 minus 7.3. We want to see the difference. And then we want that difference to be squared. And the reason for squaring it is that if we didn't square it, then all the plus numbers, the plus expecteds and all the minus expecteds would cancel out with each other. But squaring it gets rid of the negative and positive. All negative numbers squared are going to be positive, and all positive numbers squared will be positive. But then we also want to see how big that difference is relative to the expected number. So we're going to use that 7.3 in the denominator. So basically this little equation tells us a little bit about how different our data is compared to what we would have expected. We're looking at the difference between what we observed and what we expected, and then we kind of standardize that by dividing it by the expected. Well, that's just for one of the cells. So we have to do that over and over for all of the cells. This second one is going to be 3 minus 14.7. Square that, divided by 14.7. We want to do the bottom left. So plus 1 minus 12. Come on. 0.7 squared divided by 12.7, and then also the bottom right, so 37 minus 25.3 squared. I hope I wrote all these down right. Somebody's going to tell me if I didn't. Divided by 25.3. Now what that does is it gives me an idea of how far away collectively all of my actual counts are from what I expected they would be if there's no relationship between cases and exposure. If the exposure doesn't help me predict who the cases are, then there's no relationship between those two variables. So now that I've added them all up, I can actually come up with a number. That number is 43.96. It goes, on and on, but that's rounded. And what we have just done is a mathematical equation that can be drawn in a way that scares a whole lot of people. So let me draw that equation, because the whole reason that I did this is because, not because you're going to have to do this as a hand calculation. You may someday, you may have to figure out how to run this in Excel. But more importantly, what you need to know for some kind of testing scenario is what the equation is. What might be asked is, how is chi-square test of independence calculated? And the answer is chi-square is equal to, and then there's this magic Greek number, and then a bracket, observed minus expected squared over expected. So this equation right here is exactly the same thing that we just did down here at the bottom. We basically took, for each of the different cells, we said how far away is our data from what we would expect it to be if there's no relationship between those two variables. This right here is a fancy way of saying chi-square is equal to summing up or adding up all of the possible observed minus expected squared over expected. And the brackets just tells me that I do that over and over again until I have done that for every single possible cell. The other thing that you could be tested on is a concept called degrees of freedom, or simply DF. And degrees of freedom goes something like this. Let me pick a different color. If my row and column totals are considered to be fixed, so let's say I know that the total of this row is 22, the total of this row is 38, the total of this column is 40, and the total of this column is 20. How many of the numbers inside of that 2 by 2 cells are free to change, to be considered free to be any number? As soon as I put any number inside of a box, as soon as I put a number 3 in here, all of the other numbers are instantly decided, because I know that my row total is 22. If I know 3 plus what is 22, then 19 is no longer free to change. As soon as I know that 3 plus something is equal to 40, because 40 is a fixed amount, then I know that this number has to be 37. There's no other number that it could possibly be. And then as soon as I know that both this column total is 20 and this row total is 38, the only answer that can fit anymore is a number 1. In a 2 by 2 table, as soon as I have filled in one cell, all of the other cells are decided. Given that I know all of my row totals and column totals, if those are considered to be fixed, then all I have is I'm only free to change one number, and then all of the other ones are decided. So the equation then for degrees of freedom is the number of rows minus 1 times the number of columns minus 1. And so that gives me my degrees of freedom. In this case, I have 2 rows minus 1 times 2 columns minus 1. That is 1 times 1 equals 1. So I have 1 degree of freedom when I have a 2 by 2 table. In a future lesson, we'll be looking at some chi-square test of independence where we have more than a 2 by 2. Right now we're looking at this specific case where we have exposure or risk factor yes, no, and disease yes, no. So we have 2 dichotomous variables. That's always going to be a 2 by 2 table. And so in that case, we're always going to have 1 degree of freedom. So that's an explanation of how chi-square is calculated, as well as how we come up with the number of degrees for that particular analysis. Thank you for joining me for that demonstration.